Hello, I'm going to try to pin this to the screen. This is the second of two videos that we're going to go through that work with our Quadratics Chapter 4. So this is going to be Math Algebra 2, Video 2 for those who are missing class and need a little bit of a review, or for those who are getting a little bit nervous about the assessment. I'll start with some drawings for our warm-up, and we'll start with simplifying each of these expressions. So if we are looking at simplifying this first expression, we need to distribute the 2x squared is going to stay by itself. The negative 4x is distributed to 3x. The negative 4x is also distributed to the 5, and we'll wind up with 2x squared minus 12x squared plus, that's two negatives equal a positive, 20x, and we'll wind up finally with negative 10x plus squared, plus 20x. Let me try to write a little bit smaller. On this next one, we are going to warm up with another expression of using the distributive property of multiplication, 3x times x, 3x times negative 2, with a little bit more room to spare. That's 3x squared minus 3x times negative 2 is minus 6x. Here we've got a complete FOIL. Outside, inside, last, go with red. And if I start with the x's, it's x squared. Outside is 5x. Then the inside is negative 2 times x. That's going to be negative 2x. We'll combine these in a minute. And negative 2 times positive 5 is negative 10. So our final answer there for complete simplification, this will be considered standard form of a parabola, is x squared plus 3x minus 10. Same idea on this one. We'll use the FOIL method one more time, and FOIL is really just distributive and an acronym that helps you remember what you're doing. So first, outside, inside, last, we have negative 4x times 2x is negative 8x. Squared outside is negative 4 times negative 7. That would be a positive 28x. 3 times 2x is 6x. We again are going to combine those later. As a matter of fact, I'm going to leave that the way it is in the interest of space. 3 times negative 7 is negative 21. Each of these have to be distributed, and then like terms need to be added together. Ultimately, you're going to have two x squared expressions, and you're going to have two x expressions. The two x expressions will be 6x squared and 24x squared. Get you another color because you may want to stop or pause this to take more notes. This one was kind of weird from yesterday. We used this, I think it's called asteroid. So I have 6x squared, 24x squared, that's 30x squared. And 3x times negative 7 is negative 21x, plus 30x is going to be minus 9x. Here we distribute again. Let's use the distributive property. This is going to be x minus x squared. This is going to be minus 1. That'll be negative 1 and positive 2x squared. When I combine that, I've got negative x squared, positive 2x squared. I'm just left with nx squared. I have x times 1, which is positive x. And then finally, negative times 1 is minus 1. We've got a perfect square, 5x plus 3. It's the same thing as saying 5x plus 3 times 5x plus 3. And we are going to use binomial expansion for that. As soon as I can get a different color, we'll find lava is kind of a cool color. So one more time on that. This equals 5x plus 3 times 5x plus 3. I'm not going to show you the middle term. I'm just going to talk through it and then add them together verbally. 5x times 5x is 25x squared. You'll see that the same operation on the outside and inside will give us the same result. 5x times 3 is 15x. 3 times 5x is 15x. We'll make it 30x. And 3 times 3 is 9. Here's a simple distribution. The trick, I think, is to remember this negative 7. And we're going to use a term that you may not be used to. We'll start seeing that in polynomials, which is the next unit. Let's use star. That's kind of cool. Negative 7x times 5x squared. When we add exponents, it's like the x is x to the first times x to the second makes x to the third. We'll do more of a review on that in polynomials. The negative 7 times 5 is negative 35 x cubed. And then you're used to this, which is a negative times a negative is a positive, 28x squared. This is just by way of a warm-up. So we're used to talking about quadratics in both standard and vertex form. Here we have a lot of distributing going on. A binomial times a trinomial. We will have to combine like terms. Let me see if I can get back to a standard color for you to see it a little bit. Nah, let's play a little bit. So 4x times negative 2x squared, that is going to be to the third power first, plus the second power is the third. That's a negative 8x cubed. Now we have 4x times 3x is going to be 12x squared. And then finally 4x times negative 9 is negative 36x. Now we'll add our 5 terms. Negative 5 times negative 2x squared is negative 10. I'll just put it right here. X squared. This is kind of pretty cool. Please ignore that. And then we've got negative 5 times 3x is negative 15x. And then finally, negative 5 times negative 9. A negative times a negative is a positive. There's our 45. And let's add it all together. This is another way to do it, especially with polynomials. Negative 8x squared. Sorry, cubed. Misspoke. We add 12x squared minus 10x squared gives us 2x squared. Now we have negative 36x, negative 15x, negative 51x, and 45. This has 4 terms: a cubic, a quadratic, or a square term, a single x term, and our constant 45. Now's a good time to pause, or if you need to hear the verbal, just use rewind and you can see more. I'm going to move on. So this is actually Unit 4, and it's quadratic functions. I'm going to use some slideshow from this current slide. It's going to have some noise to it. Let me go back. To find the vertex and axis of symmetry of a quadratic function, then graph the function. Now here comes our noise. A quadratic function is a function that can be written in the standard form, y equals ax squared plus bx plus c. If a equals 0, it's probably going to be y equals a constant. That's just a straight line across. And that's kind of boring, so we're not going to do that. Examples include y equals 5x squared. If I had to kind of guess how to graph that, I would make it very skinny, and its vertex, because there's no horizontal or vertical translation, would be at 0, 0. Here, I have no y-intercept, which really means that the y-intercept is 0. And let me pick another color that you can actually see. Red works. So when we have that, our y-intercept, where it's going to intercept is going to be at y equals 0. And that'll be its maximum. Here we've got a positive, so a smiling parabola, but it's shifted ever so slightly to where the y-intercept is at negative 0, comma, negative 3. We would have to factor this to figure out where the vertex is. We'll get into that in just a second. So properties of quadratics. The graph of a quadratic equation, it is in the form of a U, which opens either upward or downward. Sometimes you'll hear teachers say smile or frown. The maximum or minimum point of a parabola can be at the vertex, will be at the vertex. If it's a sideways parabola, it's no longer a function. It fails both the horizontal and vertical line test. So we have here a maximum when it's downward facing and a minimum when it's upward facing. The axis of symmetry is what separates the left from the right of the parabola. Think about your own body, starting from the middle of your forehead down your nose, the middle of your mouth, your chin, right between your lungs, all the way down. You have 2 legs, 2 arms. They represent the left side of you and the right side of you. Parabola has the same thing. What separates it is called the axis of symmetry. Properties of quadratics include, we're going to find the coordinates of the vertex, the equation for the axis of symmetry of each parabola. So we're going to find the coordinates. Let's do that with a color that is not so close to violet. Right now I've got red. I think blue works. So I'm going to use the vertex. I'm going to find the minimum here, and I'm going to find the maximum here. This is a counting process. We start at the origin. I'm going down 1 and to the right 1. So 1, negative 1. You'll be asked to do this a lot on QZs as well as on the assessment. Here I'm going up 1, 1, 2. Sometimes you'll see me scallop, and to the left 1. And that value is negative 1, comma, 2. Find the coordinate points corresponding to P and Q. You can pause the video here if you'd like to do that, but they also happen to pass through integer values of our ordered pairs. Okay. I think this has animation. Yeah. Graphing a quadratic equation. Y equals ax squared plus bx plus c. Let's talk about the direction of the parabola. Is it upward facing or downward facing? If a is positive, remember it cannot be 0. Even if it is a positive very small fraction, which would make it super wide, then the graph opens up. If a is negative, even if it's a really small number, meaning it's a really big negative number, like negative 100, then the graph opens down. In the case of negative 100, it'd be very skinny. When we find the vertex and axis of symmetry, sometimes we're going to use vertex form. We first use the x-coordinate of the vertex, sometimes known as h, and x equals negative b over 2a. This is also the exact same equation for the axis of symmetry. If you're asked for one or the other, this will get you that value. Once we establish what that x-coordinate value is, we plug it into the original equation, and that gives us the value of y. In the case of the equation above, y equals ax squared plus bx plus c, if I say that x is 1 and the value of c, our constant, is 2, meaning our parabola goes through the y-axis at 2, then we have 1. So that's 1 times x squared. And we're going to say that a and b are 1. So that's 1 squared is 1, plus 1 times x, which is 1, plus 2. Y's value will be then 4. We substitute the value of x into the quadratic equation to solve for the y-coordinate, and we write the vertex as an ordered pair x, comma, y. We can use tables of values also to determine the coordinate graph, and also wherever the two y values are congruent, when we plug in x, then we're going to have our vertex. We're going to know where it hits. So choose two values for x that are one side of the vertex, either right or left. Substitute those values into the quadratic equation to find the y value, and then graph the 2 points. Graph the reflection of the 2 points on the other side, same y value, same distance away. Remember, symmetry means that your left hand and your right hand, when you hold your arms straight out, are the same distance from the center of you as the other one. So we're going to find the vertex and the axis of symmetry of the following quadratic equation, then make a table of values and graph the parabola. The direction is up. We would need to determine the vertex by using negative b over 2a. Well, negative 4 over 2 times 2 is negative 1. So our vertex would be at negative 1, and then we plug that value in to the equation. So that's going to be 2 times negative 1 squared, so that's 2, plus 4 times negative 1, which is negative 4. So 2 minus 4 puts us at negative 2, plus 3 is 1. So our vertex will more than likely be at negative 1, 1. And our axis of symmetry is also derived from negative b over 2a should be at negative 1. Let's see how we did. Actually, they didn't give us that. So I'll fill it in. Let's see what pencil does. So my direction is up. My vertex, as I talked through it, is determined by negative b over 2a, and that was going to be -1. When I plug that in, the y value is 1. The axis of symmetry is x, always x, equals -1. So it'll be something like this. Facing up, it's a little skinnier than normal, and it goes through at 1, 2, 3. Sorry, I cheated a little. This one, again, I'm going to say that the direction is negative. Come on. So down, whoa, I guess I need my pencil back. Let's go with that. That's a nice blue, I think. So our direction is down. And the vertex, again, is negative b over 2a. And that's going to equal -3 over, you'll notice there's a negative in front of the x squared. That's why it's down. So it's 2 times -1. The negatives cancel, and I get +3 over 2. I plug that in. That's going to be 9/4. So my y is going to equal 9/4 plus 9 over 2 minus 1. We can convert all of this, of course, into fourths. I'll do that out loud. 9/4 plus 18/4 is 27/4 minus 4/4 is 23/4. 23/4. So my vertex will be at 3/2, 23/4. And my axis, again, is the x value. I don't need to compute that twice. And so roughly 3/2, start there. And then we're up roughly almost 6. 1, 2, 3, 4, 5, 6. So a little shy of 6. Facing downward. And it's a regular old parabola at -1. Let's see if I can get this to work. Yep. All right, awesome. Again, pause and rewind are your friends. We'll skip this one, the more of the same, and we're going to apply this. The number of widgets the widget company sells can be modeled by the equation -5p squared plus 10p plus 100, where p is the selling price of a widget. What price for a widget will maximize the company's revenue? We know this is downward facing because of the negative. So we have something that looks like this, and we're trying to find the maximum value, which would be at the vertex. So if we're able to use our -b over a over 2a, I should say, then we've got a -10 over 2 times -5. That equals 1. And if that's 1, we'll put our x value way up here. 1. And then we plug that in for the y value. Y equals -5 times 1 squared plus 10 times 1 plus 100. So our maximum profit, what price for a widget, how much would it cost? Let's make this a dollar y value. And that's going to equal -5 plus 10 plus 100. I want to sell my widgets for $105. And now we've applied this model for selling. This is a lesson quiz, and let's go on to day 2. Again, this is Unit 4. Unit 4, Lesson 2. Quadratic functions, translating quadratics. To use the vertex form of a quadratic function, we use the vertex form is y equals a, which is the same a as we have in standard form, x minus h. H is the x coordinate of our vertex, that's squared, plus k, which is the y coordinate of our vertex. So here we are given the vertex, and we know the direction is positive. We'll just do one of these, and a better color too. Okay, so our direction, because it's a positive 2, is up. The vertex is going to be -1, so we know it's subtracting a 1. So we're already given the x value, 1. The y value is given by the k. Let me label this a little bit. A, H, K. The y value is 2. And so our axis of symmetry is x equals 2. This is going to be skinny. Our vertex is a minimum at 1, 2, 1, 2, and just about like that. All right, I'm going to try and speed past all this. Converting standard form to vertex form. So here in this example, we're given the -b over 2a for this standard form. And the standard form, the a, b, and c look like this. And I will turn my pencil back on. Okay, so here is, I need to let it know I'm actually using a pencil. Here is A. A here equals 1. B here equals -4. And C, our constant, and also our y-intercept is 6. So x equals -b over 2a means -4, so that's 4. 2 times 1 is 2, and so the x value is 2. When we plug 2 back in, we get 2 squared into our original equation, minus 4 times 2 plus 6, I have 4, minus 8, which is -4, plus 6 is a positive 2. So now that we have 2 and 2, we use our 1, so the a doesn't change. Y equals 1. I'm not even going to put it. And it's going to be x minus the h value, the x value, minus 2 plus 2, which is our k value. And now we have vertex form. We did this in a previous video, so I am looking for this next section, which is factoring quadratic equations. This brings us up to kind of a level 2 factoring, which was our day 4. If we look at the slideshow, I know that's loud, sorry. Factoring quadratic expressions, objective to find common factors and binomial factors of quadratic expressions. So a factor, if 2 or more polynomials are multiplied together, then each polynomial is a factor of the product. So factors can include 2x plus 7, times 3x minus 5. If I FOIL that out, I get 2x times 3x, which is 6x squared. 2x outside times negative 5 is negative 10x, plus 21x gives me 11x, and 7 times negative 5 is negative 35. Factors include two binomials. The product is a trinomial. It has tri or three, remember tricycle, three parts, the ax squared, the bx, and the c. You'll notice that we've slightly changed the constants, and we get a different product on the right when we do that. Factoring a polynomial reverses the multiplication. So we go from product into factors. Make sure always, your first step is to take out the greatest common factor, get it out of the way. In this case, the 7 goes into 7x squared times 7 goes into 21 3 times. It's much easier to factor than x squared plus 3 and deal with the 7 on the outside. Here we have a greatest common factor of 4, and that would be x squared plus 5x minus 3. And here our common factor is both a constant and a variable. It's going to be 3x. 3x goes into 9x squared 3x times, and 3x goes into negative 24x negative 8 times. Let's go back, and I will turn that into something you can actually take away with you. Starfield, cool. All right, so this first one, 7x squared plus 21, is the same as 7. Hopefully that's dark enough for you. 7 times x squared plus 3. The second one, I'm not feeling too confident about that color, is we're going to take a 4 out of that, and it's going to be x squared plus 5x minus 3. And for our third, we have, I'll stop messing around. I'll have that 3x out of there for you. 3x on the outside, 3x on the inside, minus 8. All right, so I'm hoping that this shows a little bit of animation. It doesn't. Our original problem is 2x squared plus 11x plus 5. We're going to look for factors of 10 because we're multiplying the a and the c. Potential factors of 10 are 1, 2, 5, and 10. And we see that we can use x plus 1 and x plus 10. 1 times 10 is 10. That's what we're looking for at first. But because of the 2 on the outside, we need to divide our constants in our binomials by 2. X plus 1 half times x plus 10 halves, which also means 5. And then we simplify the 10 over 2 to 5 and add back the 2 here on the 2x. Does that work? Can we show that when we use this, we can FOIL back to 2x squared plus 11x plus 5? That would be our check. So to check that, red's good. I'm going to take this value here. This is what I'm looking at. And I'm going to multiply the first, so that's x squared. The middle, the outside, x times 5 plus 5x. The last, so that's 5 over 2. And all of this, because we factored out a 2, is our last step. So we're going to multiply everything inside the parenthesis by 2. Pink's good. And we get 2x squared. And now we'll distribute this to the 5x plus 10x. And then 2 times 5 over 2, the 2's cancel, and that'll be plus 5. What did I mess up? Let me think. I forgot to add something. Probably outside, inside. Probably this 1/2 x. There it is. That's the 11. That's what was missing. So I forgot to add the inside. I apologize. All right. Finding binomial factors. Let's do one. I'm looking here and I've got 40 factors of 40. Do we have orange? Yeah. Factors of 40 include positive or negative 1, 2, 4, 5, 8, 10, 20, 40. Hopefully I got them all. And I'm looking for something that adds up to 14, but also multiplies to 40. So in thinking about that, since I can use two positives and I need something that multiplies to 40 and also adds to 14, the product here needs to be product will need to be 4 times 10, and the sum will need to be 4 plus 10. And so I'll use both those numbers, x plus 4 times x plus 10. I will let you pause the video if you'd like to do the FOILing and see if it equals the original equation. Let's look for something a little different here that has a coefficient, a front or a value, leading coefficient is something a little different, there we go, than actually a 1. So when it's greater than 1, my favorite tool is the tic-tac-toe method. And if I use a sharp pencil black and then apply that, what I want to do is show that a equals 2. And I'm going to use the whole thing, x squared. B equals 11x. C term equals 12. And I make a tic-tac-toe. Not very well, but, you know, you'll be doing it on paper as well. The a term goes here, 2x squared. The c term goes here, 12. The b term goes in the bottom in the box. That's how I remember everything. That's 11x. And when I multiply the a and the c, what I get is 2x squared times 12, which is 24x squared. I need terms that are going to multiply to 24 and add to 11. And 8x and 3x fit the bill. If you need to write out products, this is a great time to pause and do that in your notes. So to get there, we'll have a 2x here, and we're going to multiply up this column as well, and an x. X times 2x is 2x squared. To get across, I multiplied 2x times 4. To go across, x times 3 is 3x. And now in a different color, probably pen as well, I use jelly beans or tic-tac-toe. Remember, this is positive. Remember, this is positive. And now I have factored something that has a coefficient, a leading coefficient greater than 1, and that is 2x plus 3 times x plus 4. Please see my other videos in Otis on this. I go through this at a much slower pace. We can do the same applications with these. And now we have a special expression. This will probably be the end of the second video. If you take a hard look at these, what's missing and why is it missing? What's interesting about these is each of them is missing the b value. Remember, the standard form is going to be ax squared plus bx plus c, but it looks like what's missing is the bx. So we're going to try to look to see if we can find two perfect squares. Here we take the square root. Whoa, I don't want to do that. We take the square root of each of these values by themselves, and the square root of 4x squared is 2x, because 2x times itself is 4x squared. The square root of 49, you may remember from middle school, is 7 times 7. And why it's called a difference of squares is because we're going to have one value that's going to be plus and one that's going to be minus. And those middle terms, the outside and the inside, will cancel each other. So we'll have 2x plus 7 and 2x minus 7. Same can be said of 25x squared. That is also a perfect square whose value is 5x, and 9 whose square root is 3. And so the only thing missing is the plus and the minus, which allows us to cancel out the inside and the outside values. Other special, I'll skip the third one. The other special idea here is I can factor out the 9 and come up with something a little more elegant and easy. I call, if you don't do the GCF, if you don't pull out the GCF, it's kind of like a speed bump. So here I've got x squared, which is a perfect square, x times x. And I've also got 36 divided by 9 is 4. 4 is also a perfect square. And so I'm left with, if I use this in exponential form, I'm left with 9 times x minus 2, x plus 2. And we'll start here with the third video right here where it says end of day 3 and on to factoring these for day 4. We'll talk about some other features like solving quadratic equations using squares and square roots. And that'll get you up to speed and ready for your review in case either you're away for medical reasons or other absences, or I'm away for medical reasons like getting the COVID vaccine. You all have a wonderful Tiger Day. I'm going to try to find out where we're at, and Have a great day.